So welcome to the Money Body course. Just a quick overview first, where you find the basic information. I guess most of you have already figured out what it is. But you have the official University of Oslo website, and that's the one where you will find messages, you will find links to the educational material, etc., etc., and the link to Canvas, where you will upload the midterms. The schedule is here, and you will also find a link to textbooks, etc. So probably some of you have actually already used that option, but you can actually subscribe to these activities. So if you don't know all that, this is something which is very useful, because you will get either an email or a text in case there are changes or new information, etc., etc. The same applies to Canvas, because after the lecture, I typically send an email. So I would normally upload the link to the video here, and I normally grind the videos through YouTube because YouTube generates subtitles automatically. Now, YouTube and Google have spent a lot of money on text recognition and speech recognition, but in Money Body Physics, they haven't used many of the terms in training. So sometimes you will see some funny interpretations, like Money Body Physics was last year consequently translated into money physics, and Feynman was fireman, and so on. If you, on the other hand, take a course on machine learning, there are many words which this kind of speech recognition programs have been trained on, and they do much better. I am not going to edit those immediate speech recognition results, because that takes several hours. So I hope you can live with subtitles which have some sometimes funny errors. Okay, so this is roughly where you will find the basic, the weekly information. I also send you a text message, an email. That's the kind of standard information. So what you see here is also something which I send a weekly update with plans for next week and some reading suggestions and exercises and so on. And if you scroll down here, you will also find the link to, so everything will be on GitHub. That's where you will find the weekly slides and all the teaching material. The exercises, etc., are there. The lecture notes is something which I'm updating continuously. So don't take a too serious look at those, and rather use the textbooks and the text or the chapters which I recommend as background material for a specific week. The GitHub address, and I guess everybody's familiar with Git as a version control software. And you've all been at UIO, and it's pretty common to use a version control software. So you can actually download everything from a repository like GitHub. So you can clone all the material, and you will have all the exercises and everything. But I will also send this information through the weekly mail. And if you go into the doc folder here, you will also find the weekly slides under this pub here. If you just go to week 34, for instance, you will find a Jupyter notebook. Sometimes I will use a Jupyter notebook. Sometimes I will use a PDF. I will try to not use slides too much, but sometimes it's handy to use slides, because you want to cover some overarching motivation, and et cetera, et cetera. And like in the beginning today, I'm going to cover some basic linear algebra, which many of you have encountered. So essentially, this course is actually, if you think of linear algebra, most of what we end up doing is actually applied linear algebra in one way or the other one. This is where you find the weekly slides. And if you go back, you will find the exercises here. And 2025 is the year. And you will typically find the exercises for this week, which essentially cover some basic reminders of linear algebra, which is essential for us, like unitary transformations. You will actually see unitary transformations again and again and again. This is one of the basic operations in quantum mechanics. So the basic language is that of linear algebra, but sometimes we will also revert into calculations of integrals and solving differential equations. Okay, so that was basically where you find the information. So I wanted to change quickly now to the weekly slides. So I have prepared some slides here, and I wanted to remind you of some basic topics which we are going to cover, and also some basic topics in linear algebra. I hope you don't get offended if I go through some basic linear algebra, which is pertinent to what we are going to do here. So as we said, we will have lectures today and tomorrow. They will always be recorded. And there is a textbook which you can also access by Sabo and Östlund, which is a very popular one in quantum chemistry. Actually, quantum chemistry is theoretical quantum mechanics. We normally used to say that the quantum chemist is a misfit mathematician, physicist, and chemist. And fields like atomic physics and molecular physics are in many universities actually done within the realm of quantum chemistry. So that's a pretty common, subdiscipline, and where people have over decades done fantastic developments of many-body methods. And there is often a difference between quantum chemistry and theoretical physics, because physicists are sometimes a little bit arrogant and lazy, in the sense that when you have understood the problem, you don't care so much about the details. But when you are quantum chemistry, if you cannot deliver numerical precision or industrial precision, you don't get a job. So in chemistry, there has been a huge development of many-body method. Actually, I'd say that in the last 20, 30 years, I mean, some of the bigger developments in a popular many-body method like copper cluster theory, full configuration interaction, etc. These developments have taken place in quantum chemistry. Essentially because you need to attack systems which have many degrees of freedom, and you're also interested in the physics of reactions. So in a certain sense, if you think of inorganic chemistry, it's the physics of reactions which characterizes many of the things which are being studied. So the exercises on Fridays is something where I will just go a little bit in and out, but this is where if you want to stay and solve exercises, you can do that. If you prefer doing that somewhere else, you do that, because it can be a long day from 10 to 2 actually. So many-body methods, there's one way of looking at that and why we have so many methods. Every method represents a mathematical algorithm for solving Schrödinger's equation. So the methods which we will encounter are some of the more popular methods in many-body physics for solving the non-relativistic many-body problem. And this means essentially a Schrödinger's equation for many-body problems. And if you think of the Schrödinger equation as a differential equation, you can rewrite this, if you have many particles, as a set of coupled differential equations. That quickly blows up in proportion in dimensionality. So you will hear me repeating many times the curse of dimensionality, because the number of degrees of freedom, when you increase the size of your effective Hilbert space, they just grow dramatically or exponentially. So that means that every method deals with some kind of controlled approximation. So these methods are extremely important nowadays, because nowadays you are in situations where you experimentally can control systems at a microscopically unprecedented level. So like when I began to study physics, we were looking at, let's say, transitions among ensembles of zillions of particles. Now you can manipulate a single electron, and that means that you can test fundamental properties of quantum mechanics, like many-body entanglement. So when you are going to see many of the things I present, these will also have an eye on the type of experimental setups and physical systems which are relevant for quantum computing and quantum technologies. So we will not address these things here. But many of the things we do, the definition of basis states, computational basis, and so on, they're highly relevant for studies of these type of systems. Now, for those of you who are not fully familiar with the quantum mechanics and physical systems, there is a high level of jargon. So a lot of nomenclature and physics, which is baked in, like when I speak, I often bake in a lot of, physics interpretations. But if you're able to keep the overarching pictures in terms of the mathematics, that can actually help in then building up your insights about the equations. So the methods we cover, they can actually be used to simulate a system of what is called quantum dots and actually make a realistic simulation of a device for making quantum platforms, for making quantum gates and quantum circuits in quantum computation and quantum engineering. So the methods reflect the mathematical algorithms. So when I said coupled differential equations, that's one of the possibilities. We can set up what is called a Hamiltonian matrix in a basis. So you will hear me often use wordings like a computational basis. So computational basis is actually us finding a physically relevant basis. And then with that basis, which hopefully is a basis we can define as orthonormal and normalized, we can then use that basis as a starting point for making approximations. So if you diagonalize a so-called Hamiltonian matrix, you get all the eigenvalues and eigenstates in that specific basis. That leads to a method which is called full configuration interaction theory. And that's one of the methods we will discuss. This is a method which in principle gives you everything within an effective Hilbert space. So when I say effective Hilbert space, this is actually what essentially physics is about. Physics is to find the relevant degrees of freedom. Sometimes you can have a rigorous mathematical approach to define an effective space. And in other cases, actually in most cases, you have just to wave your arms and say that these, from experiment, I know that these are the most effective and important degrees of freedom. So full configuration interaction is a diagonalization method. You can perform a Taylor expansion around an energy, and that leads to many-body perturbation theory. And some of you will take a quantum field theory, and quantum field theory is actually, in many cases, it's used summing terms in Taylor expansion to infinite order in order to renormalize the charge of the electron, for instance. So perturbation theory is nothing but a Taylor expansion mathematically, but there are some further complexities. You can take Schrödinger's equation and you can solve the inverse problem. So this is called the resolvent. When you do that, if you look at the differential equation, when you just multiply with the inverse of the Hamiltonian, you end up with Green's function theory. So your solution is then going to be a Green's function, if you're familiar with that. That's another very popular many-body method, which links well with quantum field theory. Then you can rephrase everything as a stochastic multivariable integration, and that leads to Monte Carlo methods. And there are tons of different Monte Carlo methods. We have approximations where we can freeze out specific degrees of freedom, and we can look at the motion of a particle in a field which is set up by all the other particles. That leads to the whole machinery of mean field methods. And one of the simplest methods is called Hartree-Fock theory. And another more advanced one is density functional theory, which some of you are working with. And then we have other methods like copper cluster theory, which is extremely popular in quantum chemistry and also in other fields of physics. And copper cluster theory is actually you solving a set of coupled nonlinear equations in the unknown coefficients. So you can view the different many-body methods as just a representation of different mathematical algorithms for solving the same problem. And in this course, we're actually going to cover some of these algorithms. There's a limit to how much we can do actually in just 15 weeks. So One of the things which we are going to do today is actually to remind you guys about some basic linear algebra. We are, to a large extent, going to deal with systems which consist of particles called fermions. So fermions are spin-half particles, and the total wave function has to be antisymmetric under the exchange of two particles. That means that we can make an ansatz. So a Slater determinant is not the exact solution, but it's an ansatz which bakes in the antisymmetry. So your total wave function has to be antisymmetric, but you don't know how to bake in this antisymmetry. I should actually say that when you model Monte Carlo wave functions with neural networks, there are actually smart ways of baking in the antisymmetry without setting up a determinant. So a determinant is an approximation which leads to many of the methods which we will discuss in this course. So that's the starting point for approximating the solution of a physical system. So you will hear me again and again say, we need a computational basis. Within that computational basis, we're going to make an ansatz about the solution of the system. So ansatz for wave functions are important. So I will remind you of some of the basic algebra here. And then there are things which we will discuss, which is quite important. And for those of you who take a course in quantum field theory, you will encounter Wick's theorem, Wick's generalized theorem. This particle Hall formalism is an effective way to translate your problem into selected degrees of freedom. And it allows you to give a kind of labeling to specific types of quantum mechanical correlations. So in quantum mechanics, when we are discussing systems, we are interested in the degrees of correlations. So correlations are due to the fact that particles interact with each other through the exchange of specific forces. And these forces can be strong or they can be weak. And depending on what the forces are, you will need different many-body methods. If there are no correlations, then your wave function, your solution is typically the product, is a solution, as a solution is given by a product of single particle states. But that applies only if a single particle picture is a good picture. So these are topics which we will discuss through the semester. For those of you who may move into quantum computing, this Suzuki trotter actually is an important approximation for the action of an exponential on a many-body state. So the first really serious many-body methods we will encounter is called full configuration interaction theory. And that's based on you having a basis. And we are going to rewrite that. So Feynman diagrams are going to play an important role here, because that's a way by which we can express physical processes. So it's a pictorial way which gives us a possibility to, in a simple way with a figure, to say that this is the kind of physical process which we think is the most important. This applies to particle physics as well in quantum field theory. We are going to look at mean field theory. The main emphasis will actually be on what's called Hartree-Fock theory, which is a popular, approximation to Schrödinger's equation. And we normally call it an essential kitchen item in many-body physics, because many of the other methods actually assume that you have done a Hartree-Fock calculation. So Hartree-Fock theory, when you compare that with a full diagonalization, is something which we are going to interpret as an approximated similarity transformation or unitary transformation of the full Hamiltonian problem, where you zero out some specific correlations. Now, for those of you doing density functional theory, the electron gas in 2 and 3 dimensions is an infinite system, and that is a system which gives us the first approximation to density functional theory. And we're going to derive those equations. Then we have another method which is extremely popular in many-body physics, in quantum chemistry. It also has strong links with copper cluster theory and Green's function theory. And it's the simplest one, which is many-body perturbation theory. And for those of you doing quantum chemistry, you will probably encounter many-body perturbation theory to second order as one of the kind of basic kitchen ingredients. So when I say kitchen ingredient, that's because these are simple methods in a certain sense. I mean, when you see them the first time, you won't agree. Then we have the golden standard in quantum chemistry, which is copper cluster theory. We're actually rewriting a Hamiltonian matrix problem as a set of nonlinear coupled equations in the unknown coefficients. So you know what? When you are solving an eigenvalue problem, you get the eigenvectors. You get the coefficients of the wave function. So that's when you diagonalize. Now you can solve a diagonalization problem in a very inefficient way by rewriting everything as a nonlinear iterative process, where you start with a guess for the coefficients and then you keep iterating. That's a very inefficient way to solve a diagonalization problem. But if you truncate the problem, then you have copper cluster theory and its hierarchy of approximations. So all these kind of methods are strongly linked. I'm trying to, expose the mathematical algorithms, because when you encounter people, they will obviously say, my many-body method is much better than your method. That's a human psychology trait. But they are all related to some kind of mathematical algorithm, and they have their pros and cons. And this is one of the things which we want to expose in this course here. What are the strengths and what are the weaknesses of some of these central methods? So there's a possibility towards the end, if somebody's interested in Green's function, we have always some flexibility towards the end of the semester to change topics. Monte Carlo methods are covered by another course, and then we have quantum computing algorithms for solving many-body problems like variational quantum eigensolvers and the family of those, and they are taught in another course here. Another thing which is extremely important nowadays, which we don't cover here, but if you want to do, let's say, a special topic in many-body physics, time-dependent many-body physics plays a central role, because that deals with what we call quantum control, the way you control a quantum system over time. So if you think of quantum control, that contains 3 steps. You initializing the system. 2, you have some external probe like a laser field which acts on the system. And finally, there's a measurement part, and the system collapses to a given state. This is something you would do in quantum computing, but you would do it in every field of physics. So quantum control means actually you controlling all these 3 steps. One, where you initialize and understand the fundamental properties of the system, and this is what this course is about. So if you want to look at the time evolution, how a system evolves under the influence of some environment, then that will be the realm of time-dependent many-body physics, which we will not cover here. But that can be an advanced topic if you're interested. So for those of you who want to go into, let's say, quantum computing, or suppose you do nuclear physics and you want to model fusion or fission. So fusion is when let's say two alpha particles fuse together. So you would have 2 particles far apart from each other, and then they get closer and closer. So there's a time evolution. And then finally they fuse. That's an example of a time-dependent process, which is very difficult to model theoretically. And then you have the measurement part, which is actually another difficulty. So the textbook which we will use is the one by Szabo and Oslund, which has been a classic in quantum chemistry and many-body physics. And then there's another textbook which I often use, but there are also other ones which you will find in the textbooks, in the GitHub. So this is roughly what we plan. So one thing which we can try, I like to, so normally we do the first midterm, as we call it, around the beginning of October, because then we've gone through enough theory. And then we do the second one in the beginning of November, the first half of November. And then we have an oral examination. Now, the way I like to make the oral examination, this is just my suggestion, is that you guys make a presentation based on the projects you have done. So that means that there is no kind of nasty surprise with you having to make derivations on the blackboard and so on and so on. It's actually you make a presentation and then we ask you about what you presented. And this is often based on the theory we have discussed and also the two midterms, which normally cover many of the things we have covered in lectures. So we need to, typically what we have done is to have the final oral exam in the middle of December. So typically that week, which begins around 15th, 16th of December, because many of you are then done with the other exams. So just give it a thought about when you would like to have the final oral examination. You can also, we can have the exam via Zoom. The only requirement is that you have your camera on, so we know that's you who's sitting there. So in case you need to travel, go back home or whatever, we want to have this kind of flexibility. Any question? Practicalities? Yeah? Oh, that is you. The way we have done it is that you make a presentation of, say, 25, 30 minutes, and then we question for 10, 15 minutes, and then it's over. So it's typically 45 minutes. That's a standard oral examination here. But you prepare everything. So in a way, it's you who present the way you understood what we have done. Okay, I wanted to remind you of some basic mathematics. You have the slides, so you can actually look up everything which you see here. But I wanted to bring back some basic mathematics, which is going to be central here. So as I said, this course is actually, you can read everything in a linear algebra way in most of the methods which we're going to discuss. Sometimes we end up solving differential equations, but we can rephrase often everything in terms of some linear algebra method. So this is the way you would typically have seen a vector. And in our case, we are going to deal with complex numbers. So that means that quantities which we are going to encounter, which we will rewrite. So this is most likely the kind of notation you've seen in standard mathematics courses. So just let me know if this is something which is unfamiliar. I start counting at 0, essentially because often you write in C++ or Python. There will be some numerical exercises, but not so many. And arrays in Python begin with 0. So I guess you're pretty familiar with the inner product. And yeah, I'm just repeating some of these kind of names. So the Hermitian conjugate, often you get a little bit lazy, so you don't say Hermitian conjugate, you just say the conjugate, right? So I hope when I say this and when I'm a little bit sloppy with language, that you know exactly what it means, okay? So this is just to quickly to remind you of some of the basic things. And in our case, we will essentially deal with square matrices. And many of these matrices are going to be general invertible. And unitarity is a central part. So we are going to find a computational basis. And with that basis, we will set up unitary transformations, which brings us into another basis. And then we know that if the basis we start with is orthonormal, which is often what we select, then the new basis will also be orthonormal. That's actually one of the exercises this week. Another thing which is going to play a very central role is the outer product. So I'm just setting it up to remind you of what the outer product is of two vectors. So that's the vector multiplied with its transpose. So that's not an inner product. So the inner product is always going to be written like the one you see at the bottom here. And we are going to introduce today something which is called a projection operator. That's a matrix in practice. And that is given by the outer product of vectors. You will see that quickly now, shortly now. And a general matrix is something which I'm going to set up like this. And sometimes, so I will reserve uppercase letters. However, in my writing on the whiteboard, sometimes a boldface may not look like a boldface quantity. So I will try to have boldface quantities for vectors, lowercase letters, and then uppercase letters for matrices. And if we have a tensor, I will also define that. But to a very large extent, we will stay with one-dimensional and two-dimensional arrays, to a large extent. Now, I'm going to flash through quickly some of these things here, because these are things which you probably have seen before. And these are I'm just going to go quickly through that because I'm not going to repeat this one, but I wanted to just set up the notation for those of you who come from more mathematics, because you are most likely used to this notation for vectors, but we are going to replace that with what we will call the Dirac-Braquet notation. So this kind of notation here is actually, this one is what we will call a standard notation for vectors, which we are going to use here. And the complex conjugate is simply going to be this guy here and written like that. So just a matter of notation. And that means that the inner product is actually written like this. And this, so when you see this kind of notation here, this is a kind of physicist notation. This is actually what it means. And if you have two arbitrary vectors with the same length, then you have a general expression like that. I hope you don't get offended if I repeat some of these basic things here. Right? And this one is always a real number. And while for two different vectors, this is in general not equal. Yx is not equal to xy, which comes if you see that in the next example. Also keep in mind that the emission conjugate here is given by this quantity. And then if you take the conjugate of that one, that's equal to this one. So these are just some basic notations. And you can see the fact that x times y is not the same as y times x. If I take two vectors, first the inner product is always a real number, as you can see by this exercise. And then if you take two vectors, x and y here, you will quickly see that x inner product, xy, and yx are not the same. And that leads to a very important rule, which many of you have seen before in quantum mechanics. Yes, this is familiar, right? And clearly then the outer product of two vectors is something which we will write like this. And that is a matrix, as we know. The outer product of two vectors becomes a matrix. So just keep this definition in mind and just look them up in case you may have forgotten or they are not fully familiar. So what I wanted to do now is actually to switch over to the whiteboard and go through what I'm going to call a computational basis and some important types of operations. Okay? So let's just switch over to the whiteboard. Any questions so far about these linear algebra aspects? There is actually much more, and we are going to put in these things a little bit later. So you are going to encounter eigenvalue problems by setting up a Hamiltonian matrix and diagonalizing that one. That is going to lead to full configuration interaction theory. You're going to obviously meet my favorite algorithm again and again, the singular value decomposition. That's my favorite. That is an algorithm which is also widely used in compressing the dimensionality of the system and finding an effective Hilbert space. But let's switch over to the whiteboard. Now I need my notes here. So the problem which we are going to solve is essentially us setting up a Hamiltonian, which we haven't specified yet. So we will have a Hamiltonian operator, which I'm going to label like this. And I will normally put hats on a quantity which is an operator, just to distinguish that from other types of quantities. And what we have then is an eigenvalue problem, which I'm going to write in terms of the Dirac bracket notation. So we have an eigenstate psi of I, and then we have the eigenvalue and the eigenstate. So these are the two eigenpairs. So I'm going to use a notation here where I use psi for the solution to the Hamiltonian problem here. Now, what is pretty common to do then is actually to split this Hamiltonian into two parts or more parts. And this is a kind of basic approach which we are going to do, if it is possible. It is not always possible, but we are going to split it into two parts, one which I will call for H0, and then one which I'm going to call for H of I here. So sometimes I forget to put hats on here. So this is often called the non-interacting part of the Hamiltonian. It's often also called the non-perturbative, or the not non-perturbative, but the perturbative solution. It has many different names, and it depends on the context. But in general, I will call it the non-interacting part, non-perturbative. And this part here is called the interacting part. So the question is, why do we do this? Any good suggestions? So often your system will have kinetic energy, and the kinetic energy pertains to each particle. And we would normally label that as a part of the non-interacting Hamiltonian, right? So if you have a free particle which moves without any interactions, then the Hamiltonian would just be given by kinetic energy. Okay, yeah? Exactly. So if we are lucky, if we have a system which can be described or approximated with a Hamiltonian which offers us an analytical solution, or a solution which numerically is easy to obtain, that will define a computational basis. So I'm going to define now the solution. So often what we see, so we have physical examples, which you will encounter many, many times. So we are essentially going to look at systems which are trapped by some kind of external potential. So this H0 can often contain an external potential. So a typical external potential is the harmonic oscillator. So the harmonic oscillator is a very good approximation to many of the ways you can trap particles. Actually, if you study Bose-Einstein condensation, that is done by trapping ions by electrostatic fields, by quadrupole fields. A quadrupole field is nothing but an electric field which runs in two dimensions, like x squared plus y squared times the amplitude of the field. And that is just a harmonic oscillator. So you can realize an electric quadrupole field, which actually gives you a trap or a trapping potential, which is a harmonic oscillator. So the harmonic oscillator is something which we often encounter something similar to in nature. And the harmonic oscillator, if we now think of this as a one-dimensional case, then we know that there is and I'm going to label the states which are not the exact energies, but the energies of a non-interacting part. So this would be the E0, and then we have an E1, an E2, etc. And you can think of having one particle or more particles in these states. So these energies, epsilon I, in one dimension, they are given by the harmonic oscillator energy. where you have the frequency of the oscillator times h bar, and then you have a quantum number I. So in this case, I is equal to 0, 1, 2, and it goes to infinity. And this is I plus 1/2. And we know that when I is 0, this is just 1/2 times h bar omega. So the energy gap here is 1 oscillator unit. Now, the harmonic oscillator, I mean, you don't have, except for these quadrupole fields, you don't have ideal harmonic oscillators. So in principle, what you will have in real life is something which looks more like this. So you will have a set of states here, which are harmonic oscillator lookalike for the lowest lying states. But then you know that you reach a certain threshold here where the energy, this energy, is equal to 0. So these are normally called bound states. And these are the continuum states. And the continuum states, since then you have only kinetic energy because the particle has left the potential, then you have a continuum of solutions. So that means that you just have a kinetic energy, and in principle, you would just write this as a continuous energy here. So we normally call this the continuum. So this is a typical setup. So you could actually approximate the low-lying state, this epsilon 0, epsilon 1, etc., with a harmonic oscillator. In that case, your Hamiltonian H0 would look like something like this. And now I'm setting up in general terms. So this could be 2-dimensional, 3-dimensional, or 1-dimensional. It's just given by h squared divided by 2m, the mass of the specific particle. And then you have the gradient. And then you have some trapping potential. And then we are just going to write the potentials like a V of R. So sometimes my boldface letters don't look like boldface. I will then just put a vector sign to indicate that this is the spatial variables. So in one dimension, just have one. So this would be the non-interacting part of the Hamiltonian. Now, the nice thing with the non-interacting part of the Hamiltonian is that that often can be either solved easily numerically, or if you're lucky, it has an analytical solution. So you know the harmonic oscillator has analytical solutions. So in that case, if you look at the 1-dim harmonic oscillator, I just write HO for that one, then we know that the wave function is given by a quantum number. So you have one quantum number per dimension, and it's X, and that is given by a Hermite polynomial of degree n times X. There is a normalization factor, which I'm skipping, and then there is some E minus some alpha times X squared divided by 2. And this alpha contains the oscillator frequency and the mass of the particle. And that sets a natural length scale for the system. And then we have the energy, which then is epsilon n, which is h½ times n plus this factor of a half. So that's the harmonic oscillator problem. So that means that we have a basis, so this psi nb of x, psi of n of x, which we will often relabel. So now I'm not using the Dirac notation, Dirac bracket. I'm just setting it up as it would come out from the solution of a differential equation. Okay? So sometimes I will switch between notations like this one and the notation which you see here. Now, this basis here is an orthogonal and normalized basis. So we normally use this acronym ONB. That means that if I take a state, psi n, with psi m, this is an integral. It actually means an integral from dx minus infinity of d of x, and this is psi n of x, psi m of x. This is given by delta, a Kronecker delta, delta mn. Now, what we could do, although the harmonic oscillator is not ideal, for the system which you have here. So why is it not ideal for a system like this one? So before we take a break, so suppose your physical potential looks like that, and you can make an approximation down here. But why isn't the harmonic oscillator ideal for the type of problem which we have here? Any good suggestions before we take a small break? So how many, if you look at the harmonic oscillator, what characterizes the states in the harmonic oscillator? So we said we had an infinity of states. We have an infinity of states here. So this just goes on and on. What you have here goes also on and on. But what characterizes these states compared to these states? Discrete. Say again? Discrete. They're always discrete, but they're also always bound. A physical system is in general what we call an open system. This applies to all of physics. So sometimes the potentials can be deeply bound, but in general, the particles can actually escape. From the harmonic oscillator, you can only escape if you can tunnel through the potential barrier. So the harmonic oscillator has always bound particles. So if you want to describe a problem like this one, you could use the harmonic oscillator to represent these states, but then it wouldn't be that good for the excited states or the states in the continuum. So this is something to think of, but we can start using, since we have an orthogonal basis, we can start using that as a computational basis. But then it becomes an approximation to the physical system we want to study. So that means an ONB is what we, and now we take a small break, start point to define the computational basis. So after the break, we are going to introduce unitary transformations and how we can use that basis to actually approximate the true solution to the problem, which is the one we want here. Okay. Take a small break. Let's do that. And I went a little bit over time, but let's do 15 minutes then, right? Okay, so what we did here was to use the solution of a differential equation for a specific type of problem, in this case, the harmonic oscillator, and that defines what we are going to call the computational basis. Now, when we have such a basis, we can expand, since this is in principle, is an infinite basis, but we can then expand a new basis in terms of that basis. And this is one of the basic starting points for many of the many-body methods which we are going to deal with. So if you now think of the problem which we have, so I'm going to change a little bit the notation. So I'm going to define my computational basis, which is the solution to this non-interacting problem, is going to be given by states of wave solutions phi of I. So I goes in principle now from 0, 1, 2, in principle to infinity. Now, when we are solving problems, we cannot deal with infinities. So we actually have to make an effective space, and we would often truncate somewhere. We have to stop this set of states in order to be able to handle the problem at all, for all practical measures. But when you have such a basis, and this basis is now the eigenbasis of this operator here, the non-interacting part. This could be the Coulomb potential which you see in an atom, where you trap a given electron in an atom. And this is now given by energies, which I'm going to call epsilon phi of I. So this is a problem which we assume we can solve either exactly by finding the analytical solutions like a harmonic oscillator, or a problem which we can solve numerically pretty easily. So we can solve the problem. That's the essence here. So when we have this basis, we also know that this basis, when we now look at the inner products, this is an orthogonal, and often we use a normalized basis. This is just given by a Kronecker delta like this. Now, when we have that, we can then expand a new state. So suppose now we have this state psi of I, which is the solution to the full problem. And this has an E of I, an eigenstate, multiplied with psi of I. So just as in a parenthesis here, this H times phi of I is not equal to E of I times phi of I. So phi of I is not an eigenbasis of the full problem. However, what I can do now is to perform an expansion of phi of I in terms of a unitary transformation. And in principle, this sum here, J, runs from 0 to infinity. Okay. And then the coefficients which you have here, Uij with phi of j, these coefficients are the overlap coefficients, and these are going to be the coefficients of a unitary matrix. Does that ring a bell? So we are dealing with complex numbers, because else we would have an orthogonal matrix. So if everything was real here, this matrix would be an orthogonal matrix. So these coefficients which you see here, this Uij, they are just the overlaps between this exact state. So this is the solution to the full problem, and this specific overlap here. Now, this equation, which is pretty simple, expresses all the problems and the starting point for the methods which we're going to look at. And the reason for that is, if we have this one, there is no point to continue, because then we know the exact solution. We don't know the exact solution, which means that we don't know this one. So we have to make approximations. And all the many-body methods deal with one way or the other ones of finding approximations to this unitary transformation. So in general, if you think of this Uij as the elements of a unitary matrix, you could now think of setting up your state psi, which now contains many states, as a unitary matrix multiplied with phi. So U is a unitary matrix. Let me just quickly repeat some of the properties here. And this unitary matrix, we know that U of Hermitian conjugate is equal to the identity matrix. And we know also that U Hermitian conjugate is the same as the inverse of the matrix. And this is also equal to U of U, and that's also equal to the identity matrix. In principle, what we end up doing in all of the methods which we have, we need to make a truncation. Sometimes we have a clear mathematical recipe for projecting down to an effective Hilbert space. But in general, what we end up doing, if we now take one of these states, psi of I, which is given by the sum over j, and we have Uij of phi of j of 0, is that we end up making an approximation where we truncate the series. Where this d becomes now the dimension of our reduced space. So as I said, sometimes you have a clear recipe where you can make a transformation through projection operators which project down an effective Hilbert space. But often, when you look at a physical problem, what you would say then, if you're interested in low energy properties of a system, if you now think of here the harmonic oscillator, what you have in the harmonic oscillator, you have an infinity of states. But what you could say then is that in the problem which I'm interested in, we are only interested in the low-lying degrees of freedom. And then we simply ignore all states beyond a certain excited state. So this would be the fundamental state of the system, or the ground state. And then we can excite the system, so we could have a laser which then acts on the particle here and excites it up here or to higher states. And the whole holy grail of many-body theories is to have a rigorous mathematical approximation to the truncation which you make. Okay? So I'm just trying to set the scene here so you see how the different many-body methods pop up. So when we are going to run a FCI calculation, which is called full configuration interaction, we are going to set up a calculation in such a basis. And then to find these states, we are going to solve an eigenvalue problem in that basis. And then the eigenvectors of the problem, when you diagonalize, are going to be these coefficients here. That is full configuration interaction theory, which is the first one we are going to meet when we have gone through some technicalities like second quantization, Wick's theorem. This is just going to keep us busy the next 3 weeks, roughly. But then after that, we are going to encounter the first method, which is a diagonalization problem. And the eigenvectors are going to be these coefficients using a basis. Now, when you have a basis like the harmonic oscillator, sometimes you're extremely lucky because even the integrals can be calculated analytically. If you have a Coulomb interaction with a harmonic oscillator basis, you can actually calculate a two-body interaction between two particles analytically. And that is an extreme benefit because then that saves a lot of CPU cycles when you're diagonalizing big problems, because you can just look up a table and plug in the analytical values. So an orthogonal basis is often chosen depending on the type of physical systems you have, but also due to convenience, because sometimes you can actually have nice analytical expressions. Okay, so let's look at an example here. So suppose that we just look at a two-level system. And this brings us also in contact with quantum computing. So we assume now that there are only two levels of interest. And in this system here, we are going to ignore the spatial degrees of freedom. So we have a state, which we label with H0, epsilon 0, and then we have a state epsilon 1. So this has a state phi 1, and this has a state phi 0. Now, there's one thing I wanted to say is that when you're doing quantum computing and you're looking for a quantum platform, that means a physical system by which you can actually realize quantum gates and quantum circuits. You're actually looking for systems in nature where you have well-defined states and preferentially an excited state which has a certain lifetime so that you can manipulate it. And then you can actually, if you have many such systems, you can start to entangle them. And when you have entanglement, you have some additional benefits, which actually allows you to set up quantum gates and to translate actually the algorithms, which we are going to discuss, on a quantum computer. So a quantum computer is actually you using a physical system to solve a many-body problem. But where you, in principle, excite, you actually have gates, which are operated, for instance, by lasers or other types of manipulation, where you manipulate physical systems and perform computations experimentally. But then the holy grail in quantum computing is to find systems like this. Because in principle here, there is an infinity of other states. But you want to find a system which has isolated states which you can manipulate and which you can define experimentally. So for theorists, this is a piece of cake. So often when we discuss quantum computing algorithms, they are often disconnected from a real physical implementation. But let's now look at this system here. So what we could say now is that this state is now defined by a simple vector. So we call this a spinor, and this other one is 0, 1. Okay, that's pretty easy. And you see also now that phi 0 with phi 1 is equal to 0, because that is simply 1, 0 multiplied with 0, 1. And if you do the algebra, that should give you 0, right? And the two other cases, they give you the other two cases give you 1. If you take phi 0 with phi 0 and phi 1 with phi 1. Now, what you could do now, you could assume that this is just a model system, and you use this as a computational basis. So you define these two states here, this one and that one. This is now your computational basis. And this is what is done when you build a quantum gates and a quantum computer. So you need to find a physical system which allows you to define a computational basis. That means that you can now look at an interacting system in terms of this basis. So it means that you could now define a new state, which is a linear combination, alpha of phi 0 plus a coefficients beta, these are complex numbers, of phi 1. Now, if we go back to the definition, then this is the same as this U00, 0, and this is the same as U01. Since this is a two-state system, we have another two-state system, which will be a linear combination here, and then we have a gamma of phi 0 plus a delta of phi 1. So you could now set up a matrix here, which is your unitary matrix, which now contains this basis states U11 here. Okay. Now, there's an interesting property here. So we could now assume that this system here is now an eigenbasis of this Hamiltonian. And now we haven't specified this Hamiltonian. Phi of I. Then there is another Hamiltonian, which we now are going to calculate. So we have H multiplied with this psi of I. And this is this E of I times psi of I. So we're just repeating this exercise. And we could now think of this phi 0 and phi 1 as a computational basis. And we want then to express this solution, which we have here, in terms of that basis. Now, let's look at some other properties, because I want to introduce some technicalities first. Some technicalities, and let's set up that. So we have defined these two states. We have excluded the spatial degrees of freedom. We just defined two vectors here. So in physics, you could often think of this as the spin degrees of freedom for spin half particles. So one could be a spin up state, another could be a spin down state, if those are the degrees of freedom. But as of now, we can just think of this as two vectors. Now we can then define the completeness relation, which is given now by the identity matrix. And in this case, we have two states, I equals 0 and 1. So a Hilbert space is just given by these two states. And this is now given by the outer product, like that. And this is a matrix. So we see now that the first one gives us the outer product of 1, 0. And that simply gives us 1, 0, 0. So this is actually us setting up phi 0 with phi 0 plus, and I invite you to do that if you are a little bit rusty with calculating outer products. Like that. Now we can also define a so-called projection operator. So I can define an operator now, which I call for P. I should put a hat on top of it. And that is given by phi 0 and phi 0. I can define another projection operator, which I'm going to call for Q instead of P, with just a naming. And I define like phi 1 and phi 1. Now, there's a very interesting thing now. So what I'm doing is to anticipate something which we are going to deal with later. You can also see that Y, now 1 is equal to P plus Q. If you sum them up, because you have 0, 1 on the diagonal, 1, 0. When you add them up, you're just given back the identity matrix for this specific case. So this is a finite dimensional system. Now, these operators have a special property. If I calculate P squared, can you see what you should get? Yeah, P. And then it follows, obviously, that Q squared is equal to Q. So this is a property of what we call projection operators. These are called idempotent operators. There's another thing which is also very interesting, is that if I take the commutator, which is the same as us multiplying P with Q minus Q times P, you will see that that is 0. They are operating on different spaces. So we say that they commute with each other. Now, the reason why I bring this up is one, because I want to introduce projection operators and what they're doing, but also because we are going to use them to define an effective Hilbert space. So we will often project down or project out the lowest lying states in a system. So suppose now that we have these two states, and now I want to run calculations without including this one. So with these operators, I could now define an effective Hilbert space where I can project out via a similarity or orthogonal transformation or unitary transformation. I can project out a specific state E0 with a Hamiltonian, which is defined for an effective Hilbert space. This is something we will discuss a little bit later. But now we're just going to look at what happens if I just need to add another property. If you take P times Q, that is also equal to 0. And then obviously P plus Q is equal to 1, or the identity matrix. But now if I'm acting with this operator on phi 0, that is the same as taking this matrix, 1, 0, zeros, acting on this state, which looks like this, plus beta of 0, 1. And what you see then is that this just becomes alpha times 1, 0, which is just alpha times phi 0. So what this operator is doing is that's projecting out a specific component of the exact wave function, or what we would call the solution to this eigenvalue problem. And similarly, so we are projecting out a specific state here. Similarly, if I take Q and act on psi 0, what I will get then is simply beta times phi 1. So I'm projecting out that specific solution. Now, let me introduce another technicality, which is a tensor product, before we then move back to many-body systems. So suppose now that I have two such systems. So this brings another link to quantum computing. So if I have a system A, where I have an epsilon 0, and I put a label A here, and I have an epsilon 1. So this is a physical system A. And then I have a new physical system. So this could be one electron in a harmonic oscillator trap and one electron in another harmonic oscillator trap. This is system B. So I have epsilon B and epsilon 1 of B. Okay. So what I would be interested in now, since I have a computational basis for these systems, so in here, I have my state 1, 0. And since these are two-level systems, I can use the same states, 1, 0. I'm not putting the label A and B. I'm just skipping that one. But these vectors are the same, essentially, because we are only looking at a two-level system. So what I could do now is to make a computational basis for that system based on the computational basis I have for the subsystems. So I could now define a 2. So normally we would call this, it could be an electron, but we could also call this a qubit. So this could be, this state here could be bit 0, and this could be bit 1. If you have 3 states, it's not called a qubit, but it's called a qubit. And then you can actually build systems for quantum computing with many states than just more than just 2 states. But in general, this is the way which one has approached the system. But nowadays, there's a lot of research on using more states. But let's just stay with these simpler states here. So we can now define a we could call this a 2-particle system and its computational basis. So let's call this for phi of AB. Now, this is something which I would now define in terms of a tensor product, okay? Because now I have 2 subsystems. So I would take phi 0 of A, and I take the tensor product. So this is one possible state of phi 0 B. So I'm putting together a Hilbert space of one particle together with a Hilbert space of another particle. And this is something which I technically would write out as a tensor product. So this looks like 1, 0 of 1, 0. When you do the algebra here, just to remind you of tensor products, this takes the first one here, and it multiplies with this one. And it takes the second one and multiplies with that one. So this becomes a vector of length 4. So what you would get then is 1, 0, 0, 0. Now, often you want to have a more compact notation. So this means that you would label this as 0, 0. Because if you're writing formalism, at a certain point, you get fed up of writing this, but you want something more compact. Now, you can use these bits or these states, which you have here, to make an even more compact notation. So I could call this state 0. So it means that when I'm saving this, I have a place in memory which points to this one and that one. So this state, if we now look at it a little bit more technically, if we think of system A as x0 and system B as x1, we could then, since this is a 2-level system, a binary system, we could actually take this state here and write a formula which takes 2 times x0 plus x1. So here we have 0 plus 0, and that gives us 0. So when we are now moving on to a many-body ansatz, we're actually going to look after compact way by which we can express the states. So this is one of the reasons why I'm bringing up this. So the states which we are setting up are going to be tensor products of the Hilbert spaces of the individual states. Now you see now that you can look at another state. So I could take 0 in system A with tensor product in 1 in system B, and that is the tensor product of 1, 0 with 0, 1. And when I do the algebra, what I get then is 0, 1, 0, 0. And I would call this 0, 1. Or for having an identification, it's 1 here. And you see now that in this case, you have 2 times x0, and that is 0, plus x1, which is 1. And that gives you this number 1. So I can use the bits for this two-level system to make a compact identification of the states. So that means in memory, you would store in slot 0, this state. In slot 1 in your memory, you would store this one. And now you can continue and set up 1A and 0B, and that is going to be 0, 0, 1, 0, which we would label as 1, 0, which is again state 2. And finally, you would take 1 of A, tensor product with 1 in B. So it's a two-level system. And then we get 0, 0, 0, 1, which I would label as 1, 1. That's a compact notation. But in my memory, this would be stored as number 3, starting with 0. And what you see is that these states are orthogonal to each other, and they also normalized. So you will see now quickly that 0, 0 with 0, 1 is equal to 0, etc. So this is a new ONB basis with 4 states based on two-level systems. If you want to think in terms of qubits, you could call this a 2-qubit system. If you think of 2 electrons, this could be a 2-electron system, etc., etc. Now, keep in mind again that in principle, these systems which you have here, they do have an infinity of such states. So now we made a simple approximation where we have defined an effective Hilbert space in terms of these single particle computational basis. And now we have a 2-particle computational basis. So what you would find then, for instance, is that you could expand a state psi in terms of an alpha 0, 0 plus a beta 0, 1 plus a gamma 1, 0 plus a delta of 1, 1. Now, these states here are the solutions to this problem, 0, 0, that has some epsilon 0, 0 of 0, 0. However, the full case, this state here, is not equal to the exact energy, which we can call for 0, of 0, 0. So it means that the states which we have here, these states represent the new computational basis. And with a new computational basis, I can expand the solution to the full problem in terms of my computational basis. Does that sound okay as of now? And you see, the reason why I bring in this kind of trick, which you saw here, where you use the bit representation, is simply to have a formula which finds in which slot in memory that state is stored. Because many-body physics, the way we are going to set up an ansatz for a system is going to reflect the way we are going to store the system and to represent it in the most efficient way. So let me now try to move on to a many-body system. And our first approximation to the wave function of a many-body system. So if we take a system, so let's just plug in here, or rather a small intermezzo here, before we move on. It's a kind of small notation here. This is another technicality. Technical. This is notation. So we are going to mainly, in this course, to deal with systems of fermions. So this could be electrons, protons, quarks, neutrons, spin-half particles. It means that many of the systems we will look at, the total wave function has to be antisymmetric under the exchange of two particles. This is called the Pauli symmetry. Now, or the Pauli principle. There is, till to date, no experimental sign of breaking the Pauli principle. So people have actually tried to set up ingenious experiments where they try to see if physical systems actually break the Pauli principle. So when we are labeling a single particle degrees of freedom, we are going to have a single particle wave function, not in the Dirac notation, but it's going to be defined by some quantum number alpha, which could be spin or other quantum numbers, and some spatial degrees of freedom, R. Okay? This is a tensor product of a spatial part, which I'm going to call phi of R, and it can have some additional quantum numbers. So we would typically break this one in terms of some quantum numbers beta and some quantum numbers which deal with the spin degrees of freedom. Okay, so sigma is going to be spin, and sigma can take a value of 1/2 if it's a spin half object, and it has a spin projection of m sigma, which is plus minus 1/2. And often we label this as a spin up or spin down. So this is the kind of notation which you will see me using, which is a more compact way. So it means that there may be some quantum number beta, which we have left unspecified, which would pertain to the spatial degree of freedom. And then we have a tensor product with a part which represents the spin degrees of freedom. And then that would often break down into the value itself and the projection of m sigma. So you will often see me using a notation like this, where x now represents the spatial degrees of freedom, the coordinates, the positions of the particle, x, y, z, if you're in 3 dimensions, plus spin. So this is just a notation which I will stick to throughout the course. Now, one thing which you will find very, very irritating is often in exercises and in textbooks, they will say we omit the spin degrees of freedom because they can easily be reintroduced. That's something often which leads to some messy calculations and some irritating bookkeeping, because the spin degrees of freedom also come into play. So a state like this one, if you look at this, you would seldom write it like that, but you would often write it in a more compact way like this. And if you then use a Dirac notation, in the Dirac notation, this would often just be written like a psi of alpha and sigma like this. And sometimes it would just be written like alpha sigma. This is just another compact way. But what it stands for is you having taken into account the tensor product of two different spaces. One which represents the spatial degrees of freedom, and one which represents the spin degrees of freedom. Okay? So this is just about notations. Now, if I want to obey the Pauli principle, so one way to obey the Pauli principle is to have an ansatz for the wave function or the state of the system in terms of a determinant. We are coming back to that. So why? Let me just set up a simple determinant here, right? So let's now set up an A11, a 2x2 determinant. So think of each column now. So this could be particle 1. So this represents particle 1 along the column. And along the rows, we have specific quantum numbers. We come back to the way we do it. Now I just wanted to bring back the definition of a determinant. And these are specific quantum numbers. So this is particle 1, and this could be particle 2. What happens with the determinant if I change this, interchange the two columns? I just swap them. Yeah? Yeah, exactly. So if I now think of the Pauli principle and I use a single particle picture and each column represents a particle, if I swap the columns, this is the same as the two particles changing positions, but staying in the same quantum numbers. Then it changes sign. So a determinant could be a way to approximate the wave function of the system. So before we go into the full case, this is actually called a Slater determinant, and you will encounter that as an exercise in this week. We are going to look at some basic properties of determinants. And one thing which we will find very useful is to rewrite this determinant in terms of the number of times we can permute the columns, or the number of ways we can permute the columns. And we are going to find a representation which is going to take into account the diagonal elements only. So we are always, everything we are going to do from now on deals with finding a compact way of setting up the permutations. If I have a 3x3 determinant, I have 3 factorial. That means 6 possible ways to permute the columns. So that means that if I want to have the full anti-symmetry of the system, I would have to store 6 possible determinants. But I will show you tomorrow that you need only to store 1 and then to keep track of the permutations you can make. So we are always looking after a more compact way of representing things. This way of doing that is also going to make it easier when we are going to calculate quantum mechanical expectation values. So till tomorrow, if you want to peep into the lecture notes, you will find some material about determinants, which we are going to use to propose an ansatz for the state of the system. So we don't know the exact solution. That's why we are here. So we're going to look at methods which we can use to find the best possible approximation to the exact solution in terms of a computational basis. Whether that computational basis is meaningful or not, that depends on the physics which we are looking at. And it takes some time to develop that kind of deeper insight. So tomorrow we will start with the technicalities about determinants, and then we are going to switch to how we can use a single particle basis to make our first ansatz for the wave function of a system. Stop here, guys. Any questions? Okay, I'm just going to stop the recording here, right?